My name is JT Parr, and I'm traveling the country to interview geniuses and find out how the world works. On December 5th of 2022, the Lawrence Livermore National Laboratory achieved a breakthrough in nuclear fusion efficiency that could potentially pave the way for carbon-free energy. Laboratory Director Gordon Brunton talked me through the mechanics of the experiment and the implications of the discovery. And I got to wear a hard hat the whole time. Here's our conversation. Okay, the Big Bang, as I understand it, is there was nothing except for there was something, and that something was moving inside and outside at the same time. And in the process of it, is that entropy? Is the Big Bang Theory entropy?
Yeah, there's a lot of entropy
involved?
Yes.
Okay, so there was just like gases, and then they came together and they got so hot that it formed a atom, and then from that atom it like grew more, and then like it like was like a single thing, and then it turned into like a salamander, and then the salamander turned into a fish, and then the fish got stuck on the sand, and then it grew legs and it started talking. Can you explain to a layman what is physics?
Physics. So physics is a subset of general science. Science is kind of looking at the physical and natural world, looking for kind of observations, and then doing experiments to prove or disprove hypotheses about how things behave. Physics is a subset of science that focuses specifically on behaviors of matter and energy. And what we do here at the N.I.F is look at two specific ones in the realm of kind of temperatures and pressures. Both of those are critical in the fusion process.
From what I can gather, this is the difference between fusion and fission. Fission is how we did it back in the day. That's you take two atoms, they bang into each other super hard, and then in their like energy off colliding, they create some new stuff. Fusion is you're merging them and making them hug super, super intensely. And the energy from that hugging, in this case, it sparks units of energy.
Correct. And then it spurs on further atoms joining together, emitting even more energy, and so on and so forth.
Okay, so then off that hug is more hugs.
Correct.
And then we don't even know how far they could perpetuate.
Correct. We only burned 4% of the fuel.
It's a little bit like the movie Pay It Forward with Haley Joel Osment. Where are we right now?
So right now we're in the target bay of the National Ignition Facility. This is where all the laser beams come together in order to do an experiment on the N.I.F.
What do lasers do?
Lasers? Well, we use lasers in various contexts, but what we most recently did is we used it to start and contain a fusion process, which is the result that we achieved last December, that for the very first time in a laboratory, we achieved more energy out than we actually had to put in with the lasers.
And what are the implications of being able to do that?
So in the context of energy on the grid for the nation, what we had was a Wright brothers moment last year that set the stage for the potential of industrializing this and actually produce energy for the nation using a fusion process.
So we could, lights in the house, cell phone towers, all that could be running off of fusion?
Eventually, yes.
Oh my God, dude, it's so legit. Because one thing I've learned too is that talking to an AI scientist yesterday is he feels like the universe is an open-ended system that's constantly developing, expanding, learning new things about itself. Civilization is like that. And so he feels like when he's working on AI, he was like birthed by that, and now he's giving birth to something that will continue to do that. And you were like birthed by the sun. You're now giving birth to a new sun.
Yeah, I mean, this is constantly evolving in knowledge and understanding of what goes on in the world around us. And this is what we do on a daily basis, understand the world and the effects of all these different influences that originate back to the Big Bang of the solar system. How did we come here? Increasing our understanding of that.
Okay, so can you walk me through the experiment, like what happens from step one to final?
Yeah, so it starts with a small little seed laser in a different part of the building. It's a few picojoules. Think of a laser pointer, right? It's at that level of energy. And then it goes through numerous amplification steps in order to increase the power of each laser beam, each one of the 192, up to kilojoule level, and very high energy levels. And then all of them symmetrically at the same time arrive at a very small target capsule in the center within a few, and then the experiment happens within a few billionths of a second.
It's that fast?
It's that fast.
So the whole thing on the outside, how long does it take?
So it takes anywhere from about 4 to 12 hours to set up the laser, to align all the different mirrors, to align those laser beams down to the target chamber to super, super high accuracy. And then the actual single laser pulse that's delivered down to the chamber all happens within a few billionths of a second.
So it's over before it happens?
Absolutely.
So you're dealing with like the fundamental building blocks of reality, and you're dealing with them in like this granular sense where you're kind of playing with them and deploying them. Has that changed your like fundamental relationship to reality and how you appreciate the world?
I mean, I think for me what it does is it's the minutiae of detail necessary to make things happen, right? I mean, if you think back to the origin of the Earth, and we just explored the Big Bang, there was just this alignment of kind of very discrete and specific events that made different creatures, etc. And that is the level of precision and detail that we work on a daily basis and what is necessary presently in order to generate this fusion process. As we understand more about it, we can relax certain aspects in order to kind of make it more tolerant to the precision requirements that we currently operate under.
But that's what gets you going, is the specificity of the puzzle.
Absolutely.
And just finding the right pieces and putting them together.
Correct.
And it's been such an elaborate
kind
of process.
And many years of research that has brought us to
and you
where
guys,
we are.
so do you feel like you kind of finished the puzzle to an extent? And obviously there'll be more puzzles in front of it, but right now...
I mean, we feel that we've kind of reached the end of the beginning, right? We're on the starting blocks now, we know where to go, and we're kind of running a 100-meter sprint now. Right, exactly.
Nice. Like when you're... Can you give me an example of what you're talking about in terms of putting those specific building blocks together and the specificity that's required?
Yeah, I mean, we spoke about the Easy Bake Oven. We deliver 192 laser beams into this little gold can that's like a centimeter high. And we have to deliver with such amazing precision, both in alignment and timing. I mean, all of the laser beams hit their intended mark within about a third of the thickness of a human hair. And we have to do that repeatedly again and again and again.
That sounds awesome.
And do this 400 times a year with this level of precision. And it requires a team like we have here.
So what do you think, to a layman, what are the most pivotal aspects of this operation that we need to know about, or that would be of the most interest?
I mean, I think what we achieved in December was groundbreaking. I think whilst what we do here on the N.I.F is primarily to support a safe and effective nuclear deterrent for the nation, because the processes that we do here are very similar to what happens in nuclear weapons. But what we actually have enabled is the possibility of translating this technology into putting energy, fusion energy, on the grid for the nation in the years to come.
So these tests have implications on our weapons that we use?
Correct. The processes that go on in nuclear weapons are very similar at subscale to what we can generate here on N.I.F.
I've always wondered about that. So what is happening inside of a nuclear missile that allows it to have that process to blow up that big?
There's limited information I can actually share on that within this particular context. Many aspects of the deterrent are classified.
So you guys are funded by the government?
Correct. Funded by the taxpayers. through the government.
All right, cool. Happy to help.
Thank you so much, JT.
And what metrics do they use to evaluate your guys' like progress or potential?
So we typically agree upon near, mid, and long-term goals. Fusion ignition was one of those goals, and we kind of review our progress with our stakeholders kind of periodically and adjust the goals, just like kind of we did recently after accomplishing ignition.
And what are the different incentives at play in government-funded research versus corporate research?
Well, one of the reasons I came here and one of the reasons I stay here is that we have the unique ability within a laboratory context to work on things that are not profit-driven and so are less incentivizing to a private entity to explore. And fusion ignition was one example where there isn't an instantaneous notion of a profit that could be harnessed from that in the near term. And so this is kind of what we get to work on, that kind of is just expands new understanding in the physics realm that long term is for the greater good of kind of humanity in the world.
That's awesome. How long do you have to microwave something to get it as hot as the sun?
We generate many little stars just like the sun here every single week.
That is genuinely remarkable.
Yeah.
Like you're creating something that has
little
the heat.
star on Earth.
So what's the next step? What's the next goal?
So the next step is, we use this, the experimental facility for the purposes of stewarding our nuclear deterrent. We take experiments every day that help make sure that we have a safe and effective nuclear deterrent for the
You guys say deterrent instead of arsenal.
Correct. It's much the same. It's the nuclear weapons. And making sure that they're safe to store and they would be effectively used against any adversaries.
So you guys are running diagnostics on making sure the weapons actually work?
Correct. And we're maintaining them, modernizing them to make them kind of more effective, cheaper, etc.
So you can change what's on the inside of it?
Absolutely, absolutely. We treat it very seriously. Our job as part of our national partners is certified that if we ever had to use the nuclear deterrent, it actually would work.
Nice.
Not that anybody does.
Nobody wants to.
No. Exactly.
But it's a good way to keep it from happening.
Yes, exactly.
And so when have the fusion and the nuclear deterrent, have they always been walking hand in hand at this facility?
No, the origin of the laser really probably was the fusion process. And then what we realized is that it could be multifunctional and we could use the results, the extreme results we get in temperatures and pressures, which are similar to what happened in a weapon.
Bruno, what's up, dog?
All right.
How you doing?
Good to
That's
see
the
you,
first
bro.
chamber?
That was the first chamber. That was the first idea of doing ignition in the laboratory. And then it's just the amount of energy that comes out of it just blows everything away, and you see all these things are bent, and that's from the force of that, because it's a little nuclear explosion that happens.
What would happen if a human body was in there?
Basically, it would be instantaneously. Your body would just stop functioning.
It's a good way to go.
It would be fast. It would happen so fast you wouldn't even realize it.
Do you ever think about at the end you'll just walk in there and just go that way? Is that you?
Yeah, it's me in the picture. Looking so proud. I mean, you have to be proud when you look at that machine. It's just incredible.
Yeah, how far you guys have come and the rewards it's starting to yield. How far away do you think we are from like a practical use of it for like our energy grid?
Well, now that's a $1 billion question.
It's probably a $1 trillion question.
Or a $1 trillion question. Quite a far. The reality of this, depending upon the amount of money we invest, we probably could do it in 20, 25 years.
Okay, cool.
10 years, that sounds like a stretch, but 20 years, because there's a lot, the principle is demonstrated.
You know what's crazy? Do you feel like scientists have more optimism around the world than non-scientists?
I think we have to.
Why is that?
Because we are the innovators and we are the ones that can advance his understanding of kind of the world around us.
Yeah, I feel like most people have kind of a bleak outlook on the trajectory of civilization, but I've talked to some AI experts on this trip and now talking to you, and it's like the world's going to be full of these transformative technologies that will make our quality of life better.
We constantly
safer.
evolve.
Yeah.
From fusion, from electric cars, we have innovation all around us that
You must feel
advances
so
society.
good too that this thing that you invested your time and energy and spirit into is yielding these incredible results.
You betcha.
Okay, the Big Bang Theory, as I understand it, is there wasn't observable galaxy or universe as we understand it, but there was the existence of some kind of outside of time, outside of space, gases and energies, and that they came together and exploded, and out of that came all that we know.
And we had the conditions that surrounded all that to constantly evolve all the different planetary kind of elements that exist today. And it just so happened on Earth that we had even more that then resulted in the creation of humankind, etc.
But we still don't know where the raw materials for that.
Correct. There's much that we don't understand.
Like when you describe hydrogen, I just don't know what it looks like. Like, what is it?
It's a gas.
Okay, so it's like in a jar?
It could be.
Is it observable?
Nope.
It's invisible.
It's invisible.
That's probably why I can't visualize it.
Right. Well, the particles or the atoms are so small, they are there. If you had a microscope, you can kind of see it. But in the context of in a jar, you wouldn't be able to see it with your naked eye.
And I still don't understand why when hydrogen gets slammed together so hard it turns into helium.
Because of the pressures that are...
But why helium?
Because when you join those two atoms together, helium
Oh,
is
that's
the
like the
natural
element. And I did that in
byproduct.
science
It's the
class.
next level
When
up.
you combine certain elements and the number changes, it
Correct.
becomes
It's
another
the number that changes.
And like you explained to me earlier, elements don't ever go away. They just decompose into something else.
Or in the case of fusion,
And what you guys are
join
doing,
and
the
get heavier.
opposite natural process.
Exactly.
You guys are changing
Yep.
the way it normally runs.
Yes.
And so how do you guys scalpel that out of there?
It's again the conditions, the pressure of the fusion process.
Okay,
a
now I get it more.
byproduct is a neutron.
It's these strong force pressures that you guys put into each other that reveal the individual parts that you need.
Correct.
And then you guys can distill it from that and then make them do the things you want to create the secondary thing,
Correct.
which
energy and a neutron that then helps.
All right, I get
continue
it.
The process.
I get it.
We've made progress.
Yeah, did you want to hug or you want to slap hands?
That's like that.
I know.